I didn't catch, and everything got very beautifully erased. I'm grateful to the staff, but some formulas were lost. So we are done with this, and we are in the middle of discussing properties of localized phase. And I kind of restored, hopefully there's the same expansion of this local integrals of motion over sigmas, which are the very much original spins in your Hamiltonian, and the form of my Hamiltonian, right, is including only tau z operators, right, and quasi-local interactions between them. So now kind of this LiOM picture by me was derived, right, using assumption of locality or local response to local perturbations of MBL, right? And in some sense, it already incorporates area law entanglement into it. But what are the other consequences, right? One thing is that you have this quasi-local integrals of motion, and people call it emergent integrability, right? And emergent here is referring to the fact that these integrals of motions, I mean, if you view it positive, right, they're different in any disorder realization. If you view it negative, so far we don't have a killer construction of this local integrals of motion. So in that sense, there is no algorithm or no things that would kind of give them to you for very large system size. But it's still an operational thing, as I hope you will see, and again, maybe there will be some practical algorithms that will extract them, right? So now, if I assume that this tau z and sigma z have a finite overlap, and I believe that was pointed out by Antonello Scardicchio, it's kind of clear that you preclude transport, right? If you have a finite overlap with z, so you and let's say if sigma z is a density of U1 charge, you indeed imply localization, right? Again, this integrability is different from proper 1D integrable beta ansatz integrable models where we do know all the conserved quantities. We can write them as an explicit sums, local sums of operators, but there's also kind of where the difference is, right? That in a beta ansatz integrability, they would thermalize to the GGE in this conserved quantities, which are sums of local operators. So there, interesting phenomena includes also equilibration of densities of these conserved charges, right? You may have some, you may need to wait, right, if you create some profile of given conserved charge, right, until this conserved charge, right, would equilibrate. Now in MBL, all local integrals of motion are all integrals of motion are quasi-local, and in that sense there is no, I would kind of tentatively call it a transport channel, right? This transport channel is kind of out of the window, right? And what you have to do, right, you just have to wait till, again, system equilibrates to the GGE in this quasi-local integrals of motion, and that's something that I'll kind of discuss shortly, right? So again, there is a compare with beta dots, right? Here tau z's are local. There, right, would be sums of some finite range operators, right? And that's why, again, there is kind of, equilibration, if you wish, tau z density equilibrates on time scale order 1, right? Or time scale order, some order that may depend on the localization length, right? But it doesn't depend on the system size. And here, right, depending if you have ballistic or sub-ballistic transport, right, you may need to kind of transport, if you have some big domain wall in spin, right, you may have to wait till that spin gets transported and then get kind of smeared throughout the whole system. Right, now again, there is a kind of, it's more sketchy comment, right, but in some sense, that's something I believe that Imre also mentions extensively in his proof, that somehow this kind of integrability in spirit similar to KIM. I cannot put here any equations, right, to really back the statement up, right? But you know, the intuition would be that big perturbations, right, in MBL phase, they may cause some local resonances, right? You may need to take care of those local resonances, right? But weak perturbations have local effect, and they don't kind of kill or don't mix up your degrees of freedom far away, right? And in some sense, again, MBL relies on the absence of proliferation of resonances, right? And again, in a loose sense, right, one may see some parallels, and maybe some people see kind of much deeper parallels, and they're able to write equations, but indeed, very often this is referred, right, to kind of a KM analog. And it would be interesting and exciting if one can really make it even more precise and more quantitative. So now the last consequence, right, or some consequence I want to explore, right, is dynamics of MBL phase. And this kind of has, you know, kind of, I'm not going to do direct comparison to beta ansatz integrable systems, but just to see that these integrals of motion have some predictive power, right, and one can make some calculations using them. And you know, very kind of natural thing is entanglement dynamics, and that's actually where, you know, in some sense, I would say that was the work which kind of revived a bit the field and started this whole discussion. So you can ask about entanglement in a quench, right? So before I was speaking and discussing entanglement of eigenstates. Now it's a somewhat different setup, right? I'm starting with the product state of my spins. I of 0 is just a product state, random or maybe not so random, right? And I'm doing E minus I H spin times T, right? And I building some correlations in my state. My state is becoming correlated. And I can ask, right, if, for example, I do a bipartite entanglement, so I take this as my subsystem A, this is my subsystem B, and I can ask what is my entanglement as von Neumann entropy of system A is doing as a function of time, right? And that was done numerically, right? I think, right, it goes to Marco and others in 2008, and Jens Barderson and others in 2012. There is et al. Here. Easy to write it. So now, if you do numerics, right, you observe that Anderson insulator is kind of special in terms of entanglement growth. I'm trying just to sketch how it behaves. Here I'm putting, say, log T maybe, right? And what you are observing is that initially there is some very rapid ballistic growth of entanglement, but then system does behave differently if it's Anderson. So if I put, let's say, Jz equals 0, there's an insulator, entanglement saturates after time order 1, right, to some finite value, again, some value order 1, and it doesn't depend much on your system size, and it looks like, right, that there is some local physics at play, right? You prepared a bunch of particles, and you made your entanglement cut, and this entanglement cut, right, may cut through a couple of localized orbitals. And if you have localized orbital looking like this, right, and particle is gonna kind of spend some time in both parts of the system, it's gonna be entanglement, right? But it doesn't really depend on what's happening far away. Now surprise can come, right, when you switch on interaction and you see that upon changing interaction strength, right, your entanglement growth does something like this, right? So you approximately have very similar slope of entanglement growth, right? It grows logarithmically, and this would be some V1 interaction strength, or let's say JZ1 that is larger than JZ2, that is larger than JZ3, and so on, right? And you kind of can see how this continuously turns into Anderson, right? When you make this JZ kind of go to 0, this onset of entanglement grows, kind of goes out there in infinity, right? And you continuously connect to the answer for the Anderson insulator. Right? And that was kind of surprising numerical observation, right? That suddenly the moment you add even tiny amount of interaction, right? You can add JZ equal 0, 0, 1. You can add 1% interaction. Still, after some time, right? This logarithmic slow growth of entanglement sets in, and it continues. Moreover, right? When JZ is non-zero, right? You have again S of t proportional to log t. That's one thing, and then another thing is that S at infinity, or saturation value of entanglement, is scaling with the system size. Right? So you have a volume law saturation. Now you kind of easily can obtain both of these properties using this local integrals of motion picture, right? And here again, you can see why the interactions play a crucial role. I already mentioned that this whole picture can be built also for Anderson, right? And in the Hamiltonian, the difference is that these tau z's are going to encode your single particle localized orbitals. And the difference is that all the other terms are absent. You don't need them, right? Because it's a non-interacting system. Now, these are exactly the terms which are going to give you entanglement growth, right? And in the toy model, you can assume that you have a psi of just 2 spins, right? Just a toy example. And let's assume that this is psi, which is wave function of 2 LiOMs, actually. So I prepare actually superposition of eigenstates. If you wish, I prepare, for 2 spins, there are 4 eigenstates, right? I prepare maximally kind of mixed superposition of eigenstates, right? This is basically a sum of all eigenstates. That's my initial state, right? And then I start evolving it with my H MBL, which is in this case is going to be H1 tau Z1 plus H2 tau Z2 plus J12 tau Z1 tau Z2, right? And obviously, these terms have nothing to do with entanglement growth, and this is this whole layer which is gonna cause these 2 spins talking to each other, right? It's not very complicated. Calculate wave function. I'm not sure if I actually should be doing it. Okay, let's do it, right? Psi of t. So I just have, I'm ignoring these terms because they don't give much. They cannot produce any correlations between 2 spins, right? But there is different phase, right? Which depends if my LiOMs are pointing up and pointing parallel to each other, right? And if they're pointing anti-parallel, right? There is an opposite phase. I'm trying to draw LiOMs by fat arrows, kind of to distinguish them from conventional spins. Right, that's my state. You can calculate density metrics of, let's say, rho 1, and some things that, again, one can do calculation probably at the back of envelope, right? So it's not very complicated. I think it's going to be very nice density metrics, right? And at t equals 0, we have rho equal half, 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 half. It's normalized, it has 0 entanglement, right? Because at t equals 0, we started with a product state. And now, of course, it's a 2-spin system. We don't expect miracles. So what you'll see, right, that entanglement is going to grow to log 2 and then decay and then grow back to log 2. So it's it's a very small number of degrees of freedom. Not surprising you have finite size revivals, right? But the time scale from here, you understand what it is, right? It's basically when this 2j 1 2t is pi half, right? Exactly then you're going to have this rho being 1/2 times diagonal matrix, right? And you're going to have this S equal log 2. So that's what's happening, right? There is a time scale, which is in this case, again, is pi divided by 4j12, right? And on which you get a maximal entanglement, right? And later you have oscillation. Now, if these two guys would be happening far away from each other, you can understand, right, that this time scale, right, is going to be, again, inverse j minus 1, 1, 2, and it's going to be exponentially large, right? It's going to be exponentially large, and it's, how can we see that? Again, it's going to be x divided by something that I call psi prime, right? And idea is that you have, in a many-body system, right, you have, in the case of many spins, you have an effective magnetic field acting on a given spin, which depends on the state of all other spins, right? So I can write my HMBL to be, for two given spins, for example, tau z0, tau zx, right? And now I can write here this operator J effective 0x plus H prime, and this guy has no tau 0, tau x, right? In it. And this J effective, right, which tells me how two spins talk to each other, and is given an operator because it depends on other spins, right? It's J0x, which would be just a two-body term in this Hamiltonian, which is 10 steps away, which is this term, right? But then I'm also going to couple to all other terms on the way, right? I can couple plus, I don't know, J01 x tau z1 and then you can have more interacting terms, G01. So that's a great expression. But generally speaking, right, if you ask what is the typical magnitude of this term, right, decaying as J naught minus x divided by, again, some other length scale, which I call psi prime. And again, I need a prime here just because potentially I'm encountering exponentially many terms on the way here between these two spins, right? So even though all these J's are exponentially suppressed, in a many-body system, it's very easy to get this entropic factor. And again, it's not clear, right, if this, the intuition would be that this psi prime is bounded from above, and I believe the bound can be worked out as 2 psi, but it's not clear if they must be equal or if they are equal, or, and again, if this guy diverges doesn't mean that this guy must be divergent. So now I have the condition for an entanglement, right, spreading between spin 0 and x, such as this, right? And I may be more careful and write pi over half there, but I think in the ultimate scaling it doesn't matter because we are after a log here, right? So here we can inverse this relation, right? Plug this in here, and we are gonna have this entanglement light cone being given by psi prime log J naught t. And J naught, again, the important thing, is proportional to V at weak interactions. It may have some more complicated dependent and strong interactions, right? But it must be proportional at weak interactions if we want kind of to ensure that this thing continuously goes into Anderson, right? So that's, again, that's the intuitive explanation, or that's the explanation of this puzzling numerics, right? Which shows that as soon as you switch on very tiny JZ or V, using them synonymously, sorry, interactions. Right, now this is growth. How can we understand saturation? Right, we can understand saturation from here. Again, I want basically to say that S entanglement or S von Neumann proportional to X entanglement of T, and we are going to obtain this logarithmic growth. Now, saturation, right, and volume loss saturation also comes naturally if you think about what kind of states can you prepare in a many-body system, right? And I'm starting here, I assumed that I'm starting with some very kind of brutal superposition of all possible eigenstates, right? It's kind of pretty drastic. I'm preparing, again, equal superposition of all eigenstates of my system. This probably doesn't happen if you do such a quench, right? But the trick is that even if you do such a quench, you are preparing exponentially many eigenstates of your system, right? Because roughly speaking, locally each spin, right, is not, of course, in an eigenstate, right? And locally you are going to have some admixture of, if you expand it in the language of LiOMs, right, you're going to have some admixture of up plus a bit of down and so on, and you're going to end up with a superposition of eigenstates of exponentially many of them, but this is kind of now non-universal. That really depends on your initial state, right? You can prepare, if you wish, in a spin system, you can tilt maybe all states to be along x-axis originally, and if you have strong disorder, you know that your eigenstates are more closer to product state of in Z basis, right? And then you're going to prepare very large extensive superposition of eigenstates. You can prepare like this product state, but in any case, right, you can see that S entanglement infinity scales with S node L, and this node L is so-called diagonal entropy density. And it's a rephrasing of this fact that your ultimate entropy, right, would depend on how many eigenstates you did manage to prepare in your initial quench. And this guy can be ranging between, is going to be log 2 for this absurd quench when I'm preparing equal superposition of all eigenstates. And then for typical, let's say, quenches in a Z basis, is going to be smaller, right? So that's kind of one part of the story about dynamics of entanglement. Now we can try to translate this dynamics of entanglement to something even simpler, right? We can think about local observables. Quench. And again, I'm doing this trick, right? I want generally to understand if in such a quench, what's happening to my sigma x of t or my sigma z of t. And that's something that I can do, but I would rather first understand what's happening to my tau x of t and tau z of t. Answer for tau z of t is kind of boring. Tau z is constant, right? Tau z is an integral of motion, so it's fixed once and forever. But tau x is actually more interesting, right? Tau x is a non-trivial, and if you think, right, what's gonna be happening, right, in a tau z language, dynamics is just a precession, right? Because my Hamiltonian has magnetic field along z axis, and if I prepare, for example, if I prepare a state when tau x of 0 is equal 1, so I can try to again, and this is this somewhat extreme and maybe somewhat extreme case, right? When I'm taking 1 divided by 2 L over half, product of I from 1 to L, I'm taking equal superposition of LiOMs, or I'm taking equal superposition of all eigenstate in my system. And this is an initial state, which is equal superposition of all eigenstates, but if you understand something for that, you can understand what's going to be happening for other states as well. Right, so this is initial state in which all LiOMs on a Bloch sphere, right, I can draw a Bloch sphere with these guys, and they're all pointing in X direction. Now I prepare this guy, and now dynamics is kind of trivial, right? I have magnetic field which depends also on state of all other spins, and it's experienced by this guy, so it starts processing, right? And if I want tau x, right, tau x is nothing else but an element of a density matrix, right, of this spin. So tau x of a given spin, but let's say I is equal 1, tau x1, right, of t is twice real part of this density matrix element rho up down, right, of this spin. And this density matrix rho up down can be written also in a very nice form. So it's a sum, and here I write right. This is again sum over all configurations of all other spins, right? All configurations of tau z2, tau z3, and so on, right? And here there is an energy difference, right? It's an expectation value of my Hamiltonian when all other spins are fixed to a configuration tau, and this spin is up or this spin is down, right? Or if you wish, right, I can rewrite it as a sum of tau prime, e tau prime, e to the 2I h. I would call it h effective, acting on spin 1, right? And that's again an operator which depends on tau prime times t, right? So this is effective magnetic field from other spins. So now, again, coming back to the Anderson later case, right? Then this H effective is just H naught tilde, right? And in Anderson case, again, it's kind of a trivial result. If in an Anderson case I prepare a local eigenstate, right, or some superposition of an eigenstate full plus empty, right, nothing else is going to be happening, right? You're just going to be oscillating, and this spin will be just processing at this frequency. And it's a bit harder to think about this setup in a normal fermionic chain because of U1 conservation, at least for me. But here, right, it's really this effective spin number 1 doesn't talk at all to anybody else, and it experiences local magnetic field H tilde, so it's going to oscillate forever, and there is no actually proper thermodynamic equilibrium for this spin, right? You're going to see oscillations, and taking bigger spins, system size is not going to help your finite size effect. Right? And that's, I think, something that is expected, again, for Anderson more generically. I'm assuming that here I'm dealing with some local, I'm dealing with preparing not exactly localized particles, but this particle in an eigenstate. But if you switch to localized particles, I don't believe that the fluctuations are going to decay, right? Fluctuations are gonna stay bounded even in thermodynamic limit. Now, again, and it's expected. Non-many body system is not expected to relax, right? It is allowed, right? Because it's non-interacting, it's allowed to have this finite size revivals up to arbitrary long times. Now, when you have MBL, right, you have a range kind of time windows, right? If you wish, right, there is a different number of terms are important in this sum, right? Because there is a time window, right, which basically only next, when you have chance to talk to this spin, but haven't had chance to talk to this spin yet, right? It's going to be this time window. And then there is, again, window when you talk to two spins, but don't have chance talking to three spins yet, and so on, right? And again, this comes from the fact, right, that all this effect of H, including longer and longer range spins, are going to be exponentially suppressed, right? So there is exponential separation of time scales. Initially, I have strong enough term J12, right? And all other terms don't matter. So I'm talking to this guy. Next, longer times, there is J13, terms kick in, but then also J123, the other terms, right? And I'm talking to these three guys, and so on. And now you can really work it out in a sense that you'll see that depending on the number where you are in this time window, there's going to be some number of oscillating terms in this sum, right? And that number of oscillating terms is going to be number of terms is going to be proportional to the number of spins with whom you are talking, right? It's going to be here is going to be 2, right? It's going to be 4, and so on. So it grows as 2 to the x entangled, I would call it, right? This is the number of spins with whom you had a chance to get enough phase difference, right? You had a chance to get enough phase difference to entangle, and right, by this argument, again, one can be a bit more accurate, but if I just explain this without writing any equations, right, practically your system has a finite size, right, and you have a finite size fluctuations. And this size of your system is given exactly by this x entanglement of t, right, and then there is a number of oscillating terms, but the overall magnitude of fluctuations of this guy, right, or overall magnitude of fluctuations of this guy, right, is going to be 1 divided by a square root of the number of terms, right? So rho up, down of t can be estimated as 1 divided by a square root of d of x of t, right? And that's depends if you spin at the boundary or at the bulk. Let's say it's a spin in the boundary, right? Then you have d is basically 1 divided by 2, and then there is 1/2, and this x entanglement t, right? And now if you translate it, right, you see that logarithm in the exponent gives you power law, right? It's going to be 1 over t j naught, and here is going to be psi prime log 2. And this 2, right, or this log 2, which are the same guys, it comes again from this pretty drastic superposition of all eigenstates, right? So this log 2 is again diagonal entropy density. And then again, this log 2 is a maximal, extremal kind of case of diagonal entropy density, but more generically, right, I expect that my fluctuations of tau x of t are gonna decay in a parallel fashion to 0, right? And there is some power a, and this power a n is equal I prime s naught, right? So it's a non-universal non-universal, but it can be bounded, at least if I know what is xi prime is, S naught is less or equal than log 2 for spin systems, right? It's maximally possible entropy density. Generally, there is no universal power law relaxation of these towns. Now, again, everywhere here I was cheating, right? I was first of all preparing eigenstate, sum of eigenstates instead of a proper, as I advertised in the very beginning, I'll do a normal quench on a bunch of physical spins. That's one part where I was cheating, right, a bit. Another part when I was kind of saying that, yeah, I want this, but let me calculate this, right? But all these things can be taken care by, right? If you think about, first of all, quasi-local relation between, let's say, sigma z and tau z. So in that sense, even sigma z is going to have now non-trivial dynamics, right? Sigma z is going to be relaxing to value which is dictated by its overlap with tau z's, right? So sigma z is not relaxing to 0, it's relaxing somewhere. But then the fashion of its relaxation is going to be given exactly by other terms, right? So let's say, out of the blackboard, but if I come back here, right, if you say that, let's say, sigma z would be in the leading order some z tilde tau z, and that's going to be some constant saturation value, but then there are going to be higher order terms, right? There are going to be some term which is like C1, tau plus, tau minus, for example, right? I plus 1. And this term, right, tau plus, tau minus is exactly like tau x, tau y's. It's going to be having this power law decay, right? So again, even for physical operators, what we expect that they relax now, not necessary to 0 values, right? Relaxation value of these guys depend on the initial state, but the fluctuations are going to be all decaying in a parallel fashion. Right? And that's, again, that's another semi-explicit calculations that you can try to do with these LiOMs. Other quantities, if you are interested, may include, for example, Loschmidt echo, right? Yes. Yes. Mm-hmm. Yes. Yes. Mm-hmm. Yes. Well, again, yeah, I think there is that kappa, right, which I defined in an earlier lecture, it's transformed into this xi prime by adding some entropic factors to it, right? Because basically, again, the intuition is that, I want to bound this guy, and these guys, right, would be decaying as 1 over kappa, L over kappa, but then there are many of them. So there is potentially a correction. That's why, again, I would say that, decay of this term may be weaker than decay of the original J. Does it make sense? So, yes. Yes. Exactly, yes. And should be also directly related to the slope of the entanglement growth there. But again, the problem is that I'm trying to be careful, right? Again, maybe I'm trying to be too careful, but it's not safe assumption that all these guys are of the same order, right? Because if they would be all of the same order, right, I would say that individual J of range R is e to the minus kappa R divided by kappa, right? But then I don't know, for example, do they have really random signs or no, right? If they have random signs, I need to take some sort of estimate, would be number of terms, right? So then absolute J effective would be something like, right, number over average magnitude, right? E to the minus R divided by kappa times number of terms plus, let's say, log 2R, if it's an naive estimate, and then maybe a square root, right? And then, again, I don't really, and here I'm making some serious assumption about their statistics. And it's all kind of, since I don't want to write something that is with a very high chance wrong, right? I'm trying to distinguish different length scales, but hopefully they're all related, right? Hopefully life is nice and universal and there is not much difference. Yes, modulo this kind of constant shifts or these entropic factors. Yes? No questions? Okay. So now just as a kind of brief summary, right, of this dynamics properties, something that I tried to do, right? I tried to show that there's a logarithmic growth of entanglement. Right, and kind of its cousin, right, is power law decay of fluctuations. So say O of t minus O infinity 1 t power a. Right, these are kind of cousins which follow from the dynamics. And now I'm a bit at the fork. So if audience is interested in kind of seeing more applications, right, something that I'm happy to show how it works is, let's say, structure of entanglement spectrum. Right, which is also, in some sense, idea would be that entanglement spectrum, let's say in quantum Hall effect, right, it's very nice probe and there is a nice label for it. For example, if you have a translational invariant edge, you can label it by a momentum along the edge, right, and that gives you a way to arrange. In MBL, right, there is no real translational symmetry and there is no, in some sense, you cannot define really probe which is going to be labeling your entanglement eigenvalues, but still turns out you can use this LiOMs as a sort of statistical label. And then you can organize your spectrum by LiOMs and show that entanglement spectrum, you know, lambda k decays again also as a power law. K to some power, some other power, and that power is believed to be controlled. You know, this power can be also deduced from some of these length scales that I introduced earlier. Right, that's something that one can do, but I'm probably not gonna show this in a great lot of details. Right, I'll try to switch gears a bit and briefly discuss about, you know, something that may be kind of trying to prepare a bit ground for Roman's lectures about kind of how we can think about MBL transition, right, and what are the kind of key players, and I guess all RGs would use these players that I will be discussing as a phenomenology, and then if I have time, I can briefly discuss different open questions and maybe even discuss MBL and Floquet systems. Right. So then let's continue by omitting this entanglement business. As I was saying, right, there is these LiOMs gives you phenomenology of MBL phase and can be used to calculate certain things, but again, there is still no, in my best of my knowledge, killer algorithm kind of to construct them. And then if, you know, somebody would give me algorithm to construct them very large systems, you can really try to extract all these length scales, check if they indeed agree with each other, if these bounds are tight or not tight, and what's happening. Right, still there is a certain way of probing some of the properties, and again, matrix elements play a very important role in ETH, right? And likewise here, you can use matrix elements to probe MBL, right? And the idea is not very complicated, right? The idea is that, you know, you have this V alpha beta or O alpha beta, depends on you sandwich, right? And we know the form of this operator, right? And now we assume that eigenstates, which we take, right? They in a LiOM basis, right? They look like some product states, so they are very simple. But then, of course, if I am to use tau basis, I need to rotate this operator back to tau basis, right? So in some sense, I need to invert this relationship, right? And then I'm gonna have some terrible, there's gonna be some z tilde, tau zi, right? And then there's gonna be some c, let's say plus minus ij, tau plus I, tau minus j, and all indices are summed, and then there are going to be some more terms, right? And now here again, I'm making these guys also an operators in a sense that all these guys can depend on tau z's other than ones written here, right? So, you know, c ij plus minus is a polynomial in tau z a not equal to I or j. In some sense, that's kind of generic expansion. I'm using maybe some sort of U1 symmetry. It's also not necessary. Then you can include arbitrary plus plus, minus minuses guys there, right? So, and now, right, if you think about tau bases, right, eigenstates are very simple. Eigenstates are trivial. They're product states. Now, if I take a sandwich of this V between two eigenstates, it actually can teach me something about this expansion. It can teach me something about this. Guys, of course, the problem is, right, that before I have a proper way of constructing LiOMs, I have no idea, right, what are these labels. But still, you can use kind of a bit of brute force way of scaling, right? If you wish, I may use my system size as a kind of cutoff, right? So if I take some, let's say, imagine I take two eigenstates which are labeled like this, right? Then there is a certain, right? There is a certain number of LiOMs which got disturbed here, namely 2, right? And then I know that this is going to be basically, you know, C plus minus 1, 2 term, and then it's still a hat, so I have to kind of plug in all other tau z's. All other tau z's are being up. So by taking a matrix element, right, I am extracting one guy. Problem is that I don't know which guy it is, right? But if you think about doing this in a statistical fashion, right, what's happening is that most of the matrix elements, right, they must be flipping a lot of degrees of freedom, right? Because you know, just statistically, right, the typical matrix element is disturbing finite fraction of your spins, right? So, and then in some sense, again, that's a kind of a Pursman way, right? But I can try to think, right, that typical value of this matrix element, right, should be giving me something like this coefficient here, but somewhere high up towards the end of my expansion, right? Plus, 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 certain number of plus, certain number of minuses, right? And then again, some indices, right? And I expect this guy to be e to the minus L divided by kappa, right? And then again, this kappa and is psi minus 1 plus log 2. If I think about this, right, and now again, the kind of the idea is that we don't have really control of which LiOMs are where, but if we kind of change our system, right, there is an idea that we would expect that by this procedure, by taking matrix element, we're extracting some typical term high up there, which is kind of dominant, right? And this high up term gives us some coefficient, and we expect its exponential decay, right? And that's kind of perhaps maybe one of other ways, right, trying to extract some of these length scales present in the system. And actually, you know, there is a very nice picture of, you know, of this type of decay, right? And this type of decay is going to be very different in an Anderson insulator. Again, kind of trying to bring comparison. I think the picture actually, I took that picture right from the paper by Gorny, Polyakov, and Mirlin, right? Basically by saying that, you know, intuition about exponential suppression, right, of such a matrix element, right, would be the fact that you are in an interacting system. Because if you think about Anderson, right, this is two-body operator. And two-body operator can at most flip, you know, two fermions. That's it. But now if you have interaction, situation is different, right? So roughly speaking, you can tunnel some quasi-particle, right? But that quasi-particle can use interaction to create a lot more spin flips on its way, right? And that's kind of the intuition why in interacting system, right, this is element which flips actually a lot of degrees of freedom, it's still exponentially suppressed, right? If you think about doing the same thing in Anderson, you would have to do it many, many times, right? Each time you have to tunnel, you are allowed kind of to flip only one fermion, right? So again, the situation would be very different. Here you can have this exponential suppression, and now you can think about it, right? You can kind of come back and try to think about, you know, being consistent, right, with this notion of locality. Namely, you can try to think about taking this MBL spectrum. Yes. Uh-huh. Uh-huh. Sorry, no, L is kappa. L and this is kappa. Kappa is some length scale. Kappa, that's a kappa. This is kappa, right? And L is my system size, right? So again, as I said, I really don't know. If I would know all LiOMs, I would order matrix elements according to this distance x, right? And then would extract it in a very systematic way. But before you write such an algorithm, right, I can do finite size scaling. And I would say that in my system, in a finite size system of size L, typical matrix element must flip fraction, must flip kind of spins everywhere, right? So I'm allowed to kind of use L instead of X. Here, if I put typical here. Does it make sense? Well, C is this type of coefficient. I wrote a lot of indices, plus and a lot of pluses and a lot of minuses, because each C, right, you know, if I need to flip many L bits, right, I need to put many pluses and many minuses here, right? And again, I don't know which they are, but in order for this to be typical, right, they would be better some fraction, like 1/2 of all spins in my system. Does that make sense? Yes. Yes, exactly, yes. It means that, again, I can, you know, if my local perturbation wants to disturb my system everywhere, you pay kind of exponential price for that, right? That's, again, in some sense, somewhat synonymous to being localized, right? But I just want to see, right, what happens if I start doing perturbation here, right? And as I said, that if you take, you know, let me add some operator, right, plus GV, here, some local operator, right? And then, of course, energies of my states change because they receive leading order correction. So from E alpha, I have E alpha plus alpha GV alpha. I have diagonal matrix elements. So kind of all energies, roughly speaking, reorder, right? So I used to have, you know, my energy spectrum kind of reorders, right? It's just a leading, you know, diagonal perturbation theory, right? It's just a shift of energies. But now I can ask, imagine that states kind of have reordered, right? There are two states which were maybe originally energy order 1 away, right? These two states were order 1 energy away, but they end up being close to each other. And now I still have off diagonal terms, right? I have these terms. You can ask, are these terms enough to kind of strongly couple these states or no, right? Is there going to be resonances, and are there going to be a lot of resonances, right? There is a matrix element V alpha beta here, And if I want to be no resonances, I would better compare it to my level spacing, right? And that's something that I'm expecting if I'm in the localized phase, right? And again, if you believe those estimates, right, I would write here e to the minus L divided by this kappa, and I need to divide it by e to the minus log 2L, right? And that would be e to the minus L kappa inverse minus S or minus log 2, right? And that would be basically e to the minus L divided by this psi, right? If you believe in that relation. And now you see that in the MBL phase, right, I really expect this quantity, or I would call its log, let me call big G, log of this V alpha beta divided by delta. I expect it to be proportional to minus L, right, with some coefficient proportionality, which I may identify as some localization length. That's MBL phase, right? Then again, in Anderson, it's all going to be different, right? This whole thing, this doesn't hold, right? Because again, typical matrix elements are going to be even more suppressed. But now in ETH phase, if you remember, matrix elements were square root of the Hilbert space dimension, 1 over square root, and I'm dividing by the thing. So that's going to be, roughly speaking, it is going to grow with system size. And in MBL phase, again, it's kind of decaying with the system size exponentially, right? And this actually is something that one can use trying to define a criterion for delocalization, but that also such a configuration, why I'm kind of doing it here, right? Because I think it kind of tries to make a case that parameters, relevant parameters for you, right, indeed are these local resonances, and this kind of is an interplay of level spacing, now many by the level spacing, right, and matrix elements. And actually, these would be exactly the same two quantities that people try to use to build phenomenological RGs. Right? People try to encounter or kind of incorporate this kind of competition between local operators which want to create resonances and then level spacing, right? And it's interesting, right? Because these are kind of quite different RGs from what people have done before, because all of these guys are exponentially sensitive, right? They all expect to change exponentially with your system size, right? So that, again, kind of simple conclusion from here, right, is that matrix elements can be used and maybe indirectly probe properties of these LiOMs, right? And this gives a certain quantity whose scaling can be tentatively used to identify transition, right? So principle, at least, again, that's something that you cannot do analytically, but numerically you expect that this quantity being crossover between positive and negative scaling, right? You plot L and you plot this quantity G, and then you expect certain scaling, right? And then what you see that omega, when disorder is bigger than critical, you expect to be MBL. Quantity decays exponentially. Here it follows approximately what I promised, over to L. And then somewhere here, looks like there is a crossover. Of course, there are finite non-monotonicities. So at some point, you have this quantity G looking as if you are localizing, start going down, but then it will suddenly turn around and go up there. Right, yes? Mesoscopic, sorry? Well, I mean, I'm not sure. Sorry? Well, yeah, maybe let's discuss after the lecture ends. So yeah, so that's kind of, again, that's last bit of kind of content about properties of MBL phase, right? And the kind of small lesson from here that I tried to make, right, is that transition, right, perhaps is driven between this competition of local perturbations, of attempt, right, of local perturbations to hybridize different eigenstates, right, and level spacing, right, how one is effective or ineffective compared to the other, right? Just let me briefly kind of sketch, okay, there is this MBL phase, right? Why should we care? And one thing, right, some things which, I would call kind of MBL-enabled phenomena. Right, and that's something that, again, people did study to some extent, right, but that's something that is usually protected, and that's why, as a child, right, if scientists are kids, when you can do something that is normally is not allowed, that's pretty cool, right? So you can have infinite temperature orders, right, or orders in very high excited eigenstates, right? And that's, again, that's allowed, right? Otherwise, it's not allowed. But here it is possible because you destroy thermalization, right? For example, you can have equal infinity orders, let's say, in d equal 1. Or, for example, another kind of use of this, you can have an exponentially protected degeneracies in some topological phases. Let's say in a SPT phase, you can have exponentially protected H states. All at t equal infinity, right? And that's interesting because naively you would expect that once you start doing your SPT physics, if you go above the gap, right, in a clean system, your H states would start talking to each other very effectively, and the story ends there, right? But now, in some sense, since you are localized, you are allowed to have orders, and also, even though you go high up in a spectrum, in highly excited states, your states still, and if your excitations are localized, and you can have this exponential protected degeneracy. Something else that people have done a lot of work, right, are Floquet phases. And one example is just Floquet MBL, right? So it's a localized system which stays localized even though it's subject to a periodic driving, right? Then now kind of MBL turns out to be also useful for arguing stabilities of this time crystal phases, right? And there is also even more exotic stuff, some anomalous Floquet insulators, right? And in all these cases, right, MBL is kind of useful as a protection from heating, because generally the idea is that once you go to a Floquet system, you have subject your system to a periodic driving, right? And you expect such systems to reach eventually whatever state you are starting from. You are expecting such systems to reach an infinite temperature state, right? And MBL kind of can be used, right? If you put an MBL system in a microwave, right, you cannot warm up your lunch if your lunch is many-body localized. You subject it just to a classical periodic drive, right? MBL protects right? And some of the open questions, again, these are MBL named phenomena, right? Just to give a flavor of some of the, again, open challenges. And again, this is very, very non-generic, right? I'm sure everybody in this audience would have his own favorite list. Right? But some of these, again, include kind of delocalization, obviously, localization transition, right? Length scales, mobility edges, and these are all right. Again, LiOM construction, something else that is kind of, people already have done some work, but I think, again, still a lot of open questions remain. MBL in presence of non-abelian symmetries. And the idea is that if you have non-abelian symmetries, right, they have non-trivial representations. And these non-trivial representations, they would naively, if you just say that, oh, I have my non-abelian symmetry, and you try to work out just phenomenologically this LiOM construction and other things, you immediately see that you must have some degeneracy dictated by symmetries in your spectrum. So it means that if you have disorder plus non-abelian symmetries, like naive localization, like what I was showing here, is incompatible with such a construction. But then what happens after that, it's, I think, still open question. And if there is a universality in what happens after that, right? Either you may have a localized phase with a broken symmetry, right? Or the question is, can you have maybe something with symmetry not broken, not properly localized, but still not fully ergodic? Right? And again, I think some people in this audience worked on this. And again, examples would be some SU2, thin chains. If you're a fan of a discrete symmetries, people have done some semi-direct products of Z2. People have done S3, like permutation symmetry, which is probably one of the simplest non-abelian things one can do. That's, again, some subset of interesting questions. And let me kind of try to briefly discuss MBL in the remaining minutes. And the idea is, right, that we take a quantum system and now subject it to a classical periodic drive, which at the level of equation transforms into Hamiltonian, which depends on time, but depends on time periodically, right? And there is a pretty much canonical system of this type, right, which I probably briefly describe, right? I don't know how many of you have done Kiched rotor in 1D. No one? Okay. People are probably afraid to raise hands, but again, there is a Kiched rotor. In many aspects, also kind of very well studied, but canonical system for so-called dynamical localization, right? And those who are interested, I think it's very nicely written in the Hake book, chapter 7. And then Hamiltonian is very simple, right? It's a one, single body system. It's a p squared divided by 2 plus some coupling k sine theta, and you have a sum of periodic kicks. Delta of t minus n tau. Right, so I have a Hamiltonian. Now p with theta commute to minus IH. So this is again a quantum system. This and this guy are canonically conjugated. And you can think about this as a rotator, right? Particle on a ring. You have a angular, you have particle rotating at a different velocities, right? And this is your kinetic energy. And you periodically subject it to a kick, which kind of happens on a different basis, right? It's a momentum basis, right? This is kind of position basis, and that's what makes problem non-trivial. Now, delta function kind of allows you to write a so-called Floquet evolution operator, right? It's a unitary operator, which brings your system one period forward in time. You can have psi of t plus 1 equal to some unitary operator f times psi of t, right? And now this Floquet operator in a quantum system, basically minus I k divided by h bar cosine theta, and then minus I e squared tau divided by 2 bar. Right? So there is in exponents of two non-commuting guys. Now you can also do the same thing classically, and classically you find that this rotator kind of heats up So if you, it's natural to think about this part as your energy. Right now, again, it's time-dependent problem, so energy is not defined, but you can define energy with respect to some part of your Hamiltonian, right? And it's natural to use this as a part of energy, and the question is, you started with this particle and you keep kind of hitting it, and what is the state of this particle after a long time? Right? And the result is that classical rotator, what it does, right? It has P squared, right? Average P squared is growing diffusively. It's growing with time, and you basically heat up and it starts rotating faster and faster the more you wait. Right? Quantum system actually brings a surprise, and quantum problem turns out to be mappable to an Anderson insulator. Not quite random disorder, because you see this problem has no disorder whatsoever, right? It's this one particle problem, nothing that suggests that there may be disorder coming at you. So it's localization, but in quasi-periodic potential, right? That this problem can be mapped to, and I'm not sure if I should present it in as big details as I intended to, but intuitively, right, you try to find proper combination of your wave functions, right, and write a relation for that, right? Try to find an eigenstates of f, right? And when you try to find an eigenstate of f operator, you can map the relation for eigenstates of f operator into some problem which becomes single particle hopping. And this is done in the following way, right? So again, generally I want to write some u tilde e to the I phi u tilde is equal to f u tilde, right? I want to write my equations for the eigenstates of this local operator, right? And then u tilde can be in theta basis, right? Can be in a real space, or can be in momentum basis, right? In, call it n basis. It's a basis of angular momentum, right? And basically, idea is that p times n is diagonal, right? Is give me n h bar n, right? And turns out again that somehow both of these betas are very useful. And the trick is that by writing your kick operator, so kv divided, or v is actually cosine theta, theta divided by h bar, you can write it as 1 plus iw divided by 1 minus iw, and this w becomes tanh theta minus tanh lambda sine theta divided by 2h bar. And by choosing suitable transformation, what you can obtain, right? So this is, let me call it u plus. You can write a combination of u plus something else, right? You can write a u tilde, which is going to be, now I want 1/2 u plus e to the I phi, yes, minus h squared m squared over 2 plus. So I'm defining a function in a transformation of my local wave function, right? I just multiply it in a momentum. I just multiply it by a pure phase. And now for this u tilde, there is a very elegant algebraic relation. But now in theta basis, again, it's, I apologize for jumping between I work out some interesting combination of UM multiplied by a local operator on momentum basis, and this combination in a theta basis obeys an algebraic relation. And if I Fourier it, you see that I'm getting my hopping problem because this term is diagonal, right, in n, and the only term which is not diagonal is this omega, which is function of theta, and it gives me Em tilde m plus sum of Fourier harmonics WR UM plus R is equal to E UM. Right, so now what I have here is that I have Fourier harmonics of this guy become my hopping. Right, so this is again hopping. And you can show that it's not exactly local, but it's exponentially decaying. So I have a exponentially decaying hopping, and TMs, if you work out what it is, TM becomes tange, becomes a combination of this guy, because I have to extract W, right? And it's tange of phi minus h bar m squared over 2 divided by 2. So tange of some function, right, and h bar here, if it's not an integer number, modulo 2 pi, right, then I have some quasi-periodic potential, right, because I have tange of some m squared, and it's not going to be, again, periodic function. So now I got my disorder, which again, if you think about this, it's a bit of weird thing because changing eigenvalue phi, I'm not changing eigenvalue of the Schrodinger equation. Energy here is fixed to something else, or maybe even to 0, but I'm changing some, I'm sliding my random potential, and kicks give me hopping. And again, now you can work out that in this problem, you're going to have localization now in this kind of n space, and localization in n space means that your system fails to heat up. Right? It means that even though you keep banging, right, and trying to perturb your system, after some time, your expectation value of momentum will stop growing, and your system stops absorbing any energy. Right? Of course, localization is not the only fate of quantum systems. You can have a different single-body quantum system, and they're not going to be mappable to an Anderson insulator. But probably in the last few minutes, I want to say that similar type of considerations can be used to show localization in persistence of localization in MBL subject to an external drive. You can take an MBL system and ask, and that's kind of the first much simpler question, because more complicated question is what happens if you drive many-body localized system globally, right? But starting from a local drive, they erase. Now you can address the problem of MBL plus local drive. Right? And you can ask in a very similar fashion, you can try to say that my h of t is becoming, let's say, h MBL, some given many-body localized Hamiltonian for some part of time. And now you have a perturbation V for a different part of time. And now again, this is your period is T0, T1. And now, for example, I can take V, be some very simple operator, maybe again, sigma Z1. So I'm first leading order question is, I take my MBL system, I start driving it locally, right? Is it going to survive, right? Next order question will be if I do the same, right? That's again, that's a local drive. Global drive will be sum, let's say, of sigma Z I. Right? That's not treated here. But actually, with this local drive, turns out that you can apply pretty much the same machinery as for kicked rotor, and you can also map it to a hopping problem. And now you see that now it's going to be a hopping problem in a Hilbert space, right? So you have H0 or H MBL, right? Like here, right? These guys were part of my Hamiltonian, right? And now something that is going to induce you hopping, right, are going to be this change of my potential. But change of my potential is still a local operator if this guy is a sigma of z, because Pauli matrices are the magic matrices, they square to 1. So once you Taylor expand your change, there is nothing else that can come out of it, right? So you, in the end here, right, you still have a hopping problem. In in original eigenstate basis, in basis of HMBL, right? And hopping is given by the matrix elements of changes of this guy. Again, it's basically the same operator, right? And this order, right, is going to be given by pretty much as in the kicked rotor, right? You're going to have lambda omega as a function of this phi, and phi is again here is eigenvalue, right? It's not here, right? So you have this disorder, which is going to be change E alpha T naught minus phi T divided by 2. I dropped all H bars here, right? And now you can show that for this disorder, your level spacing is still 1 divided by the Hilbert space dimension. And we are kind of back again to the same criterion that matrix elements of this hopping potential, right, which would be here W. And here W is going to be the same. It's going to be change B times T1 divided by 2. So hopping elements of this W guy, right, between different eigenstates of original Hamiltonian are much less than the level space. That's kind of may resemble what I was writing here, right? And that is sufficient to show persistence of localization, right? And on the other hand, it shows that such thing is always going to be violated for ergodic system. If you try to play the same game with ergodic system and say that, look, I want to have my ergodic system now not heating up with respect to the local drive, again, it's not a proof that it's going to heat up, right? But you clearly see that this stuff is going to be very wrong. You're going to have actually exactly opposite relation, right? And now, again, that can be not exactly this framework, but you can extend the considerations to the case of global drive, right? And this way doesn't work to the best of my understanding, because taking such an operation for this guy is going to lead pretty terrible non-local operator, right? But there are other ways to handle. I think Wojciech, François have done some of the work. You can try to work out a sequence of canonical transformation to diagonalize Hamiltonian subject to a global drive. Or from the other hand, you can try to do some sort of Landau-Zinner type of estimates to get, in each case, you get a criterion, right, which says that at weak or fast drives, or actually both, in some sense, your drive needs to be not too slow, right, and not too strong, many-body localization can survive the global driving as well. Right? And that's, again, interesting because it gives rise to all this MBL protected stuff in Floquet case, which I already raised. So I'll just probably stop here and ask for the questions.
Nice lectures, and I assume there are some questions.
So just understand the statement concerning this last part, so that if you have MBL state and you drive, so the statement is that localization will be preserved if driving is not too strong or so? What are conditions?
Well, again, I think here actually you're protected. In principle, you are protected parametrically by, you know, I would say that naively, right? If you have a local operator if you drive many-body localized phase, right? I think at any drive strength, at eventually large systems, this condition will be satisfied, because you know this guy is proportional to driving strengths, but there is kind of exponents at play here. So whatever is your driving strength, again, naive guess would be that the local driving, many-body localized system is going to survive arbitrary local driving, right? But for global drives, of course, that's not correct. For global drives, there are pretty stringent relationships saying that, again, how weak your drive must be and how fast you must be driving. But that also depends, okay, that a bit depends on if you're driving with, if you have a pulse drive, because in some sense, pulse drive is a bit more dangerous, right? If you think about such drive, you don't have a single frequency, right? You would have the whole spectrum of such a drive. And if you have, on the contrast, harmonic drive, right, when you just have a single frequency and there is a given kind of frequency on which your driving is capable of inducing resonances, or multiple of this frequency, right? You can have whatever, omega, 2 omega, 3 omega. So there are different conditions, but in any case, I think for that situation, there is a finite range of stability.
Very good. So, Abhishek.
Subrato wants to ask us something.
Okay, so I mean, maybe you already said it, but so based on this LiOMs, I mean, what can you say about the off-diagonal elements like in the MBL phase?
Well, that's what I was trying to say here, right? I was trying to relate this scale, right, which popped up in the among the scales describing MBL phase, right, and saying that, you know, things are consistent if I take this scale and compare it to the level spacing. In the end, I have here is exactly the same Xi that I was defining in the first lecture. This is the same Xi which controls the rate of the unitary. And then when this, you know, once this Xi is finite, you may expect some sort of decay. When this Xi diverges, right, I would expect kind of crossover to delocalization. And that's no proof, right? Not a proof, right? But I hope that is this clear or not really.
So I mean, so it looks like they're still quite small, right? I mean, like maybe. So
Quite
they're
small.
still like the off-diagonal elements. They're still 1/.
Oh no! In MBL phase, they're even smaller than in the ETH, right? Again, there is this ratio of diagonal matrix element to the level spacing, and the criterion would be for the ETH, right? If you plug in Srednitsky ansatz, you're gonna see log 2 by 2 with L increasing. But here, again, the idea would be that as soon as it is not decreasing, you are in trouble, because your local perturbation will start inducing resonances, and that, again, I cannot say, you know, we don't know if that's exactly the mechanism of the localization, but if you, let's say, do numerical studies, you would see that this crossover between these two behaviors
Yeah.
So, okay, there's one
So
question.
how
way
much
up
is
there.
known about whether MBL survives in driven dissipative systems? When you have both a drive and you have a coupling, so that there's dissipation in the system. How much is known about whether MBL survives in such a scenario? What kind of dissipative mechanisms, and is that something which?
Well, I think that's something. It's not okay. Oh, okay. Okay, that's something that certainly people thought about and worked on. I would say that probably the slightly more precise formulation of the question should be what signatures of MBL survive, because intuitively, right, once you stop being in an isolated system, right, you have dissipation comes from coupling to some bus or some external world, right? So you may hope for some signatures of localization or some kind of remnants to survive. But again, I don't think at this point it becomes a localization. It becomes an open system right? But
Right, something like the imbalance or something, I guess, is what you might look at.
yes, and my understanding is that first of all, if the coupling to some bath is weak, right, that also defines some time scale, and below, you know, of course, there is a crossover phenomenon, right? That before you see your bath, you will behave and look like you are localized. And okay, I cannot exactly comment on what's gonna be happening once you. What can be the exact statements, let's say, about thermodynamic limit or long infinite time limit once you switch on coupling to the best? But I believe that there are works by some people in the audience here who claim that there is, again, there are some signatures which survive.
Right.
Yeah, any more questions? Well, that's not the case. So let's thank Maksym for this lectures.